So here are problems 3, 4, and 5, some problems that, for the main purpose of, people are wondering, well, what's the right thing to put down? Because in a number of these, it requires different calculations. All right, so in this first problem, when you try to go through the whole system of what things, the normal approaches to finding limits, we plug in the 1, and we get 1 over 0, which is not indeterminate form, by the way. It's 1 divided by 0 is just the normal blowing up of the world, not like 0 divided by 0. That's independent. So what we then say as we go through the graphing, that we say, all right, we can't do any of those, all of those fail, so let's try to approach it numerically. What we do know is that the denominator is 0 at x equals 1, so that means there's an asymptote, okay, likely an asymptote there. So that means all we have to do is test to the left and to the right here, and so we would say, what is the value of we're going to evaluate the function just to the left and just to the right of 1. So here we have 0.9 divided by the natural log of 0.9. And here we have 1.1 divided by the natural log of 1.1. And you're saying, but I don't have my calculator. Okay, not necessary, because you guys know your natural log function and what it looks like. The natural log function looks like this. With x equals 1 here, it's an asymptote on x equals 0, and then goes here where we know that the natural log of 1 is 0. Okay? What this tells you is that at x equals 1, that's the magic point. That's the place where the natural log turns from negative to positive. Okay? And that's why this question was asked, because this is the key. So with this, the top number is positive. The bottom number is the natural log of 0.9, which is a negative. Therefore, this is going to approach negative infinity as we were to go to coming in from the left. Likewise, 1.1 on the other side ends up being a positive divided by a positive. So this implies that the graph of this function is going to go towards positive infinity on the right. That's why then the answer to this is does not exist. Okay. Numerically, this is the only way to really do this one. You've got to be able to think through it. However, you can do number 4 numerically, but this would be probably the preferred way. I'm going to approach this as a product. So look at this. This is the same as the cosine of x multiplied by 1 over x squared. Okay, so I'm going to do this one analytically, which is a preferred approach if it works out. So the limit of a product equals the product of the limits. So I can do the limit as x approaches 0 of the cosine of x, and then multiply it by the limit as x approaches 0 of 1 over x squared. And cosine function is a continuous function at x equals 0. The cosine of 0 is 1. The limit as x approaches 0 of 1 over x squared is infinity. So the final answer is infinity. And that's an analytical approach. You can still use this approach and it'll still work. Okay, that's just a little bit easier to follow. And finally, number 5, we're given this piecewise function. And for x not equal to a, it's this thing. And then for x equals a, it's 0. So which one of these are true? Well, does the limit as x approaches a of f of x exist? Well, let's go find out. So the limit as x approaches a of x squared minus a squared over x minus a, what is that? Well, let's go figure it out. We can factor the top So this becomes the limit as x approaches a of x minus a times x plus a all over x minus a. The x minus a's cancel. So this becomes then the limit as x approaches a of x plus a, and we start all over again. And we can plug in the a. So we get a plus a, or we get an answer of 2a. So the answer to the first one is yes, and the limit is 2a. The second one, does f of a exist? Darn right it does. It's 0 by the definition of the piecewise function. And then is f of x continuous? Well, that's a big no, because these first two have to equal. This would be the correct way to say it. We say that this is false, and the reason is that the limit as x approaches a of f of x is not equal to f of a. Mathematically, that's the best way to then say it, to wrap it up. Make sense? Okay. So, you know, the whole point of the problem sets is to continuously learn how to do this. If you're really focused on what I've been trying to say for the whole quarter so far, is that this is a year-long process. I'm just expecting that by the end of the year, you are way better than you were at the beginning of the year at being able to do this. And it's not just about the individual markings. That's the only way I can figure out, are you making progress or not? So, but, you know, in all honesty, if you look at your work and you compare it to maybe the first couple that you did, you'll notice that most of you have improved dramatically in your written mathematics, which is really good. And you're going to only get better. So, that's good. Libby, I said most of you. Okay. Well, pull out your notebook then. We are going to have day 2 of implicit differentiation. All right, I have 3 problems on the back board. We are going to handle those one at a time. They both have a variety of things within them that we're going to have to figure out. And I'm going to actually do then a quick recall of why we're doing what we're doing. So let me start with that. See if this makes sense. If I tell you that I'm thinking of a function, I'm going to call it f of x, and I'm going to say that it's equal to y. So y is equal to some function. Okay? And if I say, all right, now that I have this function, let's find the derivative of it. Okay, so now watch what we would do. We'd say, well, we would take the derivative of the left side, and we would take the derivative of the right side. So that would mean I would take the derivative with respect to x, because this has x's in it, and we take the derivative of the right side. Yes? I'm going to show you. I'm going to show you. I'm going to show you why it looks like it does. Because we've been just doing it, right? Now I'm going to show you why it comes from that. So look at the right side first. F of x, the derivative of f of x, does everybody agree that I can write that as f prime of x? Ding, 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 just like that. Okay? The notation then is, see, if we have y and we take the derivative of y with respect to x, this is why we write it then as dy dx. Okay, this is where it comes from, dy dx. Now, it's technically not true, but you can think of this as I'm shifting the y, and I'm moving it up here. So then it's dy dx, where this y right here is this y right here. Okay, we actually use this notation when we take a look at with other letterings. For example, if I have some function w is equal to g of t, okay, using all different letters, and I say take the derivative of this, I would say, well, we'll take the derivative of the right side or the left side, and we'll take the derivative of the right side. Notice I put d dt because it's the derivative of that thing, whatever it is, with respect to t. Then we write this as dw dt, and we write this as g prime of t. Same exact thing as this, just different letters, so you can see how it transfers. See the connection? Okay. Now, this means that whenever I ask you to find the derivative of y, the derivative of y is dy dx. And that is implicit into this kind of problem. Okay, so, all right, let's go do this. X cubed minus y cubed equals 4. This is the graph of that. Okay, this is x cubed minus y cubed, and I have the a value at 4. So what we're going to do is we're going to write the formula for the slope of the line tangent to this graph at any x value. That's what the end result of this is. Okay, let's do this. And we're walking. Okay, so derivative of the left side and the derivative of the right side. That's the whole point. So I'm going to do this, and I'm going to do this. The derivative of the left side. Now, this is the derivative of a difference, so I can take each derivative individually. So the derivative of x to the third with respect to x is 3x squared. Now, let's see if you remember what we started yesterday. Minus, what is the derivative of y to the third with respect to x? 3y squared times dy dx. Okay, this had to do with the chain rule where we say that the y is the outer function, and so we're thinking of it as 3 times y to the second and then times the derivative of the y, which is dy dx. And so the derivative of 4 is 0. Now, this is the calculus where we found the derivative. Now we just have to solve for dy dx. It should make sense that if the y was embedded in the original equation, then the dy dx is embedded in the derivative. Okay, so now we just solve. So what do we got here? I got negative 3y squared dy dx is equal to negative 3x squared. And then solving for dy dx, that's the goal. Find the derivative. Dy dx is equal to negative 3x squared divided by negative 3y squared. And I guess I'll summarize it over here. That means dy dx is equal to x squared over y squared. Make Make sense? Okay, so let's just experiment. Okay, we're just going to experiment a little bit here. And unfortunately, I don't have actual values for this, which I guess we could. Yeah, let's do this. Let's pretend we're going to do it at x equals 1. Okay, so we're going to test this. We're going to test this for x equals 1. Okay, we're going to test this for x equals 1. What is the derivative when x equals 1? Okay, well, dy dx, and I'm going to show you a new notation here. Dy dx, and I want it evaluated at x equals 1, but do you see that I also need the y value? Okay, so that means I got to plug in x equals 1 into the original. I'm going to rewrite this here. I got 1 cubed minus y cubed equals 4. And then doing a little manipulation here, I got y cubed is equal to negative 3. So if y to the third is equal to negative 3, then y is equal to the cubed root of negative 3. Remember, it's legal to do cubed roots of negatives, not square roots. Okay? Now, all right, cubed root, punch it in your calculator. Just give us some values here. Give us something. It's about equal to 3, 3, 3, 6, 25, 6, 0.6, 0.7 something. Negative what? Negative 1.4. Negative 1.4 to the third power gives you negative 3. Okay, so about negative 1.4. We're just estimating here. So I want to know what the slope is. Well, look at this. This is the new notation. dy dx, and then I'm going to draw a vertical line here. And I'm going to write x equals 1 and y equals the cubed root of negative 3 is equal to. This is new notation. This vertical line stands for evaluated at. The vertical line stands for evaluated at. So I'm going to say dy dx evaluated at x equals 1 and y equals the cubed root of negative 3 gives us, let's see.
Why is it written like, yeah, one thing with the why can't you like?
They put it at the bottom. That's the way they write it.
Why?
That's the way it is. I think they tried to put them up here and then they just fell down. So
Gravity.
gravity. So it's 1 squared divided by this cubed root of negative 3 squared. See what I'm doing here? I'm using the derivative formula right here. And so what do I get? I get 1 over, now give me, let's see, 1.4 squared, negative 1.4 squared, what is that? 1.96. So it's 1 divided by 1.96. And so that's pretty close to a half. 0.5? 49? I don't know. I'm estimating it because that's about 2. See? Negative 1.4 squared, or the negative cubed root of 3, or the cubed root of negative 3, that quantity squared should become about 1.96. Were you agreeing with these numbers? Or they just, okay. Just making them up. So the slope, it says it's about a half, okay? So how good is that? I don't know. How close is that to a half? So, go fix that, Megan.
No.
You're in charge.
No.
Okay. So look at here. My x equals 1. That. Okay. So what was the whole goal here? The goal was to test whether or not that derivative of x squared divided by y squared gave us the for this wacky equation when x equaled 1. And that's pretty doggone close. The visual that connects with the algebra that we did over there. Okay. All right. So we took our time on that one. Now let's do a couple of crazy ones. Let's do number 2, and I'm going to do that one up at the front here. Now, I'm modeling for you how to do these types of problems, but obviously it's impossible for me to show you how to do every one. So that's why you have to just learn how I'm going about this. Okay, the relation is x times y is equal to the cosine of y. And we're out to find the derivative of it. I actually did put this in here, so let's take a quick peek at it. This is what it looks like. So this is a kind of a fun one. It wiggles up and down the top, okay, but you can't see it too well until you get, so can you see the wiggling? It goes back and forth up the top. So x times y is equal to cosine of y. All right, let's do this. So the derivative of the left side and the derivative of the right side, okay? So what's the derivative of the left side? So I'm going to write it like this, and you can get in the habit of writing this, or once you do enough of them, you don't have to do that anymore. What's the derivative of x times y? Who said it? Brandon said. This is a product, okay? So we have to do the product rule on x times y, okay? So here we go. What's the derivative of x times y? Well, let's do it. So we'll let x be the derivative first. So it's 1 times y, okay, because the y sat out, plus, now the x has to sit out, and what's the derivative of y? dy dx, always. That's the answer to the left side. That's the derivative of x times y. We had to use the product rule. The light bulb moment there. All right, right side, derivative of the cosine of y. It's the negative sine of y times dy dx. Starting to see it? See. Okay. Now that's the calculus part. We took the derivative of both the left and the right side. The algebra part says solve for dy dx. Okay. So I don't know what's the best way. What I'm going to do is I like to throw all my dy dx's on the left side, everything that does not contain a dy dx on the right side. So what I'm going to do is I'm going to move this one to the left, I'm going to move this one to the right, and this one's going to stay where it is. So here we go. The sine of y times dy dx plus x times dy dx is equal to y. I move this term to the right side by subtracting it. And I move this term to the left side by adding. And then the middle one stayed the same. See the algebra there? Okay, now I did that because I'm going to use our algebra technique of factoring out the common term, which is the dy dx. So I'm going to pull out a dy dx out of both. So I'm going to pull out this one and pull out this one. So what am I left with? I'm left with the sine of y plus an x is equal to negative y. We're solving for dy dx because that's the derivative. So it's dy dx times this thing is equal to negative y. So then all we have to do is divide by this term right here. So dy dx is equal to negative y divided by the sine of y plus x. And that's your derivative. Piece of cake. Okay. Product rule. Bam, 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 solve for dy dx. Okay, next one, number 3. The sine of x divided by y is equal to x. So the sine of x divided by y is equal to x. Okay, what notion crosses your mind? Chain rule and quotient rule. Okay, so here we go. What's the derivative of the sine of something? The cosine of the something. So it's the cosine of x divided by y, but then multiplied by the derivative of the something. So we have to find the derivative of x divided by y. And that's a quotient rule. X is on the top, y is on the bottom. So here we go. You know the quotient rule by heart, don't you now? Bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay. This is us applying the quotient rule to the derivative of x divided by y. And we have a dy dx that's buried inside of there that we're going to have to solve for algebraically. Okay, derivative of the right side is 1. So how on earth are we going to get at that x, that dy dx that's in there? We can get rid of this one by dividing both sides by it. We can also get rid of the y squared by multiplying both sides by y squared. And then, so let's do that first and then see where that takes us. So, and then I'm going to simplify. Y times 1 is 1 minus x times dy dx is equal to y squared over the cosine of xy, x divided by y. I multiplied by y squared and both sides and divided both sides by cosine of xy. Can you see it? This is just algebra. Okay, solve for dy dx. And so, well, that just means it's a two-step problem. You learned two-step equations back in 8th grade. Subtract my y and divide by negative x. So, negative x dy dx is equal to y squared over the cosine of xy minus y. That's the subtraction of the y. And then divide the whole thing by negative x. dy dx is equal to, and when I do it, I'm going to do each one of them. So it's going to be y squared over negative x cosine of x over y minus plus, that is, y over x. Okay. That is a pretty complicated equation, and its derivative, this is the derivative, which means for any given point on that weird-looking graph, you can find the slope of the line tangent by plugging in the x and the y for the point that's on the graph. Piece of cake. All right. Let's do the infinity. Let's do infinity. So, what does infinity look like? Infinity is this one. And my a is 4. My a is 4 here. I need another board. All right, here we go. I just want to make sure that it is 4, because we're going to test this one if we can. So a is 4. So infinity. 4 times x squared plus y squared squared is equal to 100 times x squared minus y squared. Ah, this is easy. Infinity divided by, no. It's the infinity example. Yes. See this right here? See the picture? See the graph? This is the problem. It's the infinity example. Okay. All right. Well, let's do it. Okay, left side. We're going to find the derivative of both sides. How do we handle this thing on the left? Everybody look at this. It's a chain rule. I don't know about you, but when I see this, when I look at this, this is what I see. I see 4 times something squared. That's how I visualize it. I can see the big picture, the biggest Russian doll. So I'm going to use a chain rule on the outside. So this is going to be 4 times 2 times x squared plus y squared to the first power. Okay. Multiplied by the derivative of what's inside. So it's going to be 4 times 2 times x squared plus y squared to the first, multiplied by what? You tell me. 2x plus 2y times dy dx. That's the left side of the equation. Now we have to do the derivative of 100 times x squared minus y squared. How do we do that? Yeah, technically you could do a product rule where 100 is the first function, and then x squared minus y squared is the second function. I wouldn't do it that way. I would distribute. This is the same as 100x squared minus 100y squared. And that's so much easier. So all I did was distribute the 100, and now I'm going to find the derivative of that. So this is equal to, I'll put it here. Let's see, a derivative of 100x squared is 200x minus the derivative of 100y squared is 200y to the first times dy dx. No problem. Okay. All right, well, let's just clean this up a bit and see if we can get anything good that comes out of this. 8 times x squared plus y squared times, oh, I guess I suppose I could pull out a 2 there, x plus y times dy dx is equal to, as long as we got that 200 there, let's take the 200 out. 200 times x minus y times dy dx. Do we agree? Okay, maybe just clean up a little bit more. I spy 16 times x squared plus y squared times x plus y dy dx is equal to 200 times x minus y dy dx. Now, we can solve for dy dx because if we wanted to write this as an actual derivative, we would go through the algebra to solve it. What it would require, take a peek here. This is a binomial times a binomial, so we would have to do FOIL on this. Okay, get all those terms individually, multiply this back together, so then we get all individual terms, and then we have our dy dx terms, and then we would just solve for those. So it's doable. Wonder if there's any known values. Oh yeah, look at this. 0. I wonder what it's going to do with that. Because look at, the slope could either go here or the slope could be here, but the coordinates are the same. So I have no idea what it's going to do. Okay, so we're going to plug in 0, 0 and see what happens. It wipes out. Doesn't it? Because y times, this is going to be 0 times this. This is going to get 0 times this. So it doesn't give us, it's going to give us 0 across the board. 0 equals 0. We broke it, is right. And I don't see how that would be impacted anywhere else. Huh. Well, let's pick a different value. Maybe not. I got to look back at that one. I'll look at it. Okay. Are you understanding how this is working? Yes. How come I could do the chain rule? This one? Well, it's just this term times this term. There's no power here. Yeah, you can do 1 times 100 and then multiply by the derivative of this, which ends up being exactly the same as this. It'll still work. It'll give you the same thing. Now, tomorrow, we're going to find the second derivative of an implicit graph. And your homework on this section is due Friday.